two teams of scientists set out to answer the same question. How fast is the universe expanding? Both used methods that have been trusted for decades. Both checked their work, refined their instruments, and checked again. Both are almost certainly correct. However, their answers don't agree. One says the cosmos is stretching at one speed. The other says it's stretching 9% faster. That gap should not exist. For more than a decade now, it has survived every attempt to explain it away. Every calibration revisited, every source of error hunted down and eliminated. The discrepancy hasn't faded, it has sharpened. Scientists call it the Hubble tension. It sounds modest. It is not. Because if neither measurement is wrong, then something about the universe itself, something woven into the fabric of space and time and energy, does not behave the way physics says it should. The model that has described the cosmos for nearly a century may be missing something fundamental. And right now, no one knows what it is. If you're ready, hit subscribe and let's begin. It begins with a single number, not a particularly famous one, not a number most people would recognise or think twice about. It does not appear on classroom walls or in popular science headlines, but it quietly governs almost everything we think we know about the cosmos. The age of the universe depends on it. The size of the observable universe depends on it. The distances between galaxies, the timeline of cosmic history, the ultimate fate of everything that exists, all of it traces back to one value, expressed in a unit so specialised that most people outside of astronomy have never encountered it. Kilometres per second per megaparsec. That is the language of the Hubble constant. What it describes is deceptively simple. A megaparsec is a distance, roughly 3.26 million light years, or about 30 million trillion kilometres. For every megaparsec of space between us and a distant galaxy, the universe is stretching, carrying that galaxy away from us at a certain speed. The farther the galaxy, the faster it recedes. Not because it is flying through space like a bullet from a gun, but because the space between us is growing, everywhere, in every direction, all at once. The universe is not an explosion scattering debris outward from a central point. It is a fabric, and the fabric itself is stretching. The Hubble constant is the rate of that stretch, and almost everything else in cosmology flows from it. Get the number right, and the age of the universe emerges naturally. The distances to the most remote galaxies snap into focus. The timeline of cosmic history, from the first atoms to the formation of stars and planets, and everything that followed, falls into a coherent sequence. The story of existence gains a beginning, a middle, and a trajectory that can be traced forward. Get it wrong, even slightly, and the consequences cascade. A universe that appears to be 14 billion years old might turn out to be 12. The observable universe might be larger than we thought, or significantly smaller. Distances that seemed settled become uncertain. The map we have drawn of reality shifts beneath our feet. Events that appeared to fit neatly into the timeline no longer belong where we place them. Stars form too early, galaxies appear too quickly, and the physics that was supposed to explain it all starts to buckle under the weight of its own predictions. This is why the Hubble constant has never been just a number. It is the scaffolding on which the rest of the picture hangs. Move it, and everything moves with it. For most of the 20th century, pinning it down was one of the great obsessions of observational astronomy. Not because the number itself was glamorous, but because nothing else in cosmology could be settled until it was. The age of the universe could not be determined. The distance to the edge of the observable cosmos could not be calculated. The density of matter, the geometry of space, the balance of forces shaping the future of everything, all of it waited on this single value. Careers were staked on it. Bitter rivalries formed around it. For decades, two camps of astronomers defended wildly different values with unwavering conviction, each certain the other had made a fundamental error. The arguments were public, sometimes deeply personal, and lasted longer than many of the careers involved. Reputations were built and damaged in the pursuit of a rate of expansion that most of the world had never heard of. That history matters now because the fight never truly ended. The instruments improved, the methods sharpened, the uncertainties shrank to levels that would have seemed miraculous 50 years ago. But the disagreement did not vanish. It changed shape, shed its old arguments, adopted new and more precise ones. And today, it has returned in a form more stubborn, more statistically significant, and more consequential than anything that came before. The number is once again in dispute, and this time, the stakes are not just a matter of calibration. They reach into the foundations of physics itself. To understand how we got here, we need to go back to the moment the universe first revealed that it was moving at all. For most of human history, the universe was still. The stars drifted in their slow arcs. The planets traced their wandering paths. But the stage on which all of it unfolded, the cosmos itself, was assumed to be fixed, permanent. A backdrop that neither grew nor shrank nor changed in any fundamental way. Even Albert Einstein believed this. When his own field equations of general relativity, published in 1915, suggested that the universe should be either expanding or contracting, he found the implication so unsettling that he introduced a new term, the cosmological constant, specifically designed to hold everything in place. The mathematics allowed for a universe in motion. Einstein insisted it was wrong. The first evidence that it was not came from an unlikely figure. Vesto Slipher was a quiet, meticulous astronomer working at the Lowell Observatory in Flagstaff, Arizona, in the years before the First World War. His project was modest by the standards of the time. He pointed a spectrograph at faint, blurry smudges of light scattered across the night sky, objects then called spiral nebulae. No one knew what they were. Most astronomers assumed they were clouds of gas somewhere within our own Milky Way, unremarkable and close. Slipher was measuring their spectra, recording the wavelengths of the light they emitted, looking for patterns. What he found was strange. Almost every one of these objects was redshifted. Their light had been stretched toward longer wavelengths, a signature of motion away from the observer. They were receding, not one or two of them, nearly all of them, in every direction he looked. Whatever these faint smudges were, they were fleeing. Something was pushing the universe apart, or the universe was pulling itself outward, and either way the cosmos was not standing still. Slipher published his results over several years. The astronomical community, consumed with other questions and other egos, largely failed to notice. Thousands of miles away, a Belgian priest and physicist named Georges Lemaitre did notice. Lemaitre was both a man of faith and a man of rigorous mathematics, and he saw in Slipher's redshifts something no one else had articulated. In 1927, he published a paper that drew a line between Einstein's general relativity and Slipher's observations. His conclusion was radical. The universe is expanding. Not objects hurtling through empty space, but space itself stretching, carrying every galaxy, every star, every atom embedded in it outwards, like points drawn on the surface of a balloon being slowly inflated. He derived a proportionality between distance and recession velocity directly from the field equations and matched it to the data. Theory and observation aligned. His paper appeared in the Annales de la Société Scientifique de Bruxelles, an obscure Belgian academic journal published in French. Almost no one in the English-speaking scientific world read it. 2 years later, Edwin Hubble provided the proof that made expansion undeniable. Working at the Mount Wilson Observatory above Pasadena, California, Hubble had access to the most powerful telescope on Earth, the 100-inch Hooker reflector. He had already achieved something extraordinary with it, demonstrating that the spiral nebulae were not clouds of gas within the Milky Way, but entire galaxies, vast independent collections of billions of stars at distances so enormous they reshaped humanity's understanding of scale. Now Hubble went further. Combining his own distance estimates with Slipher's redshifts, he showed that the farther away a galaxy was, the faster it appeared to be moving away from us. The relationship was linear, clean, unmistakable. Distance and velocity were locked together in direct proportion. That proportionality, the rate at which recession speed increases with distance, became known as the Hubble constant. Lemaitre had predicted it from theory. Slipher had measured the redshifts that revealed it. Hubble provided the distance measurements and the institutional authority that made the scientific establishment pay attention. History, as it often does, attached the discovery to the name with the biggest telescope and the most prominent institution. Lemaitre's contribution was not widely acknowledged until decades after his death. Slipher's data, which underpinned the entire finding, was rarely credited at all. But the discovery belonged to all three of them. A quiet observer in the Arizona desert, a priest physicist in Belgium, and a man with the world's largest telescope in California. Between them, they overturned a picture of the universe that had stood for millennia. The cosmos was not fixed, it was not permanent. It was growing, stretching, evolving, and it had been doing so since the beginning. And the number at the heart of that discovery, a single constant describing how fast the fabric of reality is coming apart, would become the most contested and most consequential value in all of modern cosmology. Knowing the universe is expanding was the breakthrough. Measuring exactly how fast, that was the problem that would haunt astronomy for the next century. To calculate the Hubble constant, you need two pieces of information for every distant galaxy you observe. The first is its velocity, how fast it is moving away from us. This part is elegant. The redshift of a galaxy's light gives you its recession speed directly, encoded in the stretched wavelengths of the photons it emits. It is one of the cleanest measurements in all of astronomy, and it has been refined to extraordinary precision. The second piece is the distance, and here the elegance ends. There is no way to measure the distance to a galaxy the way you might measure the distance to a neighbouring town. Light does not come stamped with a return address. It arrives, faintly, from across unimaginable stretches of space, and the challenge of determining how far it has travelled is one of the oldest and most difficult problems in the physical sciences. The universe, simply put, does not come with a ruler. So astronomers built one. Not a single instrument or a single method, but a chain of them, each one reaching further than the last. Each one calibrated against the one that came before. They call it the cosmic distance ladder, and everything we know about the rate of expansion depends on it. The first rung is parallax. As the Earth orbits the Sun, nearby stars appear to shift very slightly against the background of more distant ones. The principle is the same one that makes a finger, held at arm's length, appear to jump when you close one eye, then the other. The amount of apparent shift reveals the distance. It is purely geometric. It makes no assumptions about the star itself, its colour, its brightness, its age, just angles and trigonometry. But parallax has a limit. Beyond a few thousand light years, the shift becomes too small to detect, even with the most sensitive instruments ever built. The nearby universe submits to geometry. The deeper universe requires something else. That something else is the standard candle, an object whose true brightness is known. The logic is intuitive. A lantern on a distant hillside looks dimmer than the same lantern held in your hand. If you know how bright the lantern truly is, the degree of dimness tells you how far away it sits. Scale that principle up by a factor of billions, and you have the method that carries astronomers from the edges of what parallax can reach to the farthest visible structures in the cosmos. The most important standard candles in this story are Cepheid variable stars and Type 1a supernovae. Cepheids are aging giant stars that pulse, brightening and dimming in a steady, repeating rhythm. What makes them extraordinary is that the period of their pulse is directly tied to their true luminosity. A cepheid that beats slowly is genuinely brighter than one that beats fast. Measure the rhythm and you know the brightness. Compare that to how bright the star appears and you know the distance. It is a relationship first discovered in 1912, and it remains the backbone of the distance ladder to this day. Type 1a supernovae reach further still. These are thermonuclear explosions, white dwarf stars that accumulate matter from a companion until they cross a critical mass threshold and detonate. Because the trigger point is nearly the same every time, the peak brightness of these explosions is remarkably consistent. They are, in effect, identical detonations scattered across the universe, each one a beacon visible across billions of light years. They are the final rung, the one that stretches deep enough into the cosmos to measure the expansion itself. But every rung of this ladder stands on the one below it. Parallax calibrates the Cepheids. Cepheids calibrate the supernovae. If any rung carries an error, a miscalibrated brightness, a systematic bias, an overlooked source of contamination, that error does not stay contained. It climbs. It propagates upward through the entire chain, quietly distorting every measurement that follows. The cosmic distance ladder is both the most powerful tool in observational cosmology and one of its most vulnerable. Its strength is its reach. Its weakness is that every rung must be right for any rung to be trusted. And it was a single discovery more than a century ago that made the whole structure possible. The discovery that made the cosmic distance ladder possible came from someone who was never allowed to touch the telescope that gathered her data. Henrietta Swan Leavitt worked at the Harvard College Observatory at the turn of the 20th century, one of a small group of women hired to do the meticulous, repetitive labour of cataloguing stars from photographic plates. The observatory called them computers. The work was exacting. The recognition was minimal. The pay was 25 cents an hour. Leavitt had studied astronomy at what would become Radcliffe College, and she was, by all accounts, an extraordinarily careful observer. But in the rigid hierarchy of early 20th century science, her role was to measure and record, not to theorise or interpret. The telescope was not hers to use. The questions were not hers to ask. She asked one anyway. Leavitt had been assigned to study variable stars in the small Magellanic Cloud, a companion galaxy to the Milky Way, visible from the southern hemisphere. Variable stars are stars whose brightness changes over time, some in irregular bursts, others in clean, repeating cycles. Among the latter were a class called Cepheids, stars that brighten and dim in a steady, predictable pulse, like a slow heartbeat of light. Leavitt catalogued dozens of them from the observatory's collection of photographic plates, each one a glass negative capturing a tiny patch of sky on a particular night. She compared plates taken weeks or months apart, tracking how each star's brightness rose and fell, recording the length of each cycle with painstaking precision. It was work that demanded patience far beyond what most people could sustain. Leavitt had it in abundance. In 1912, she published what she had found. The pattern was striking. The brighter a Cepheid was, the longer it took to complete one pulse. The relationship held across every star she measured. It was not approximate. It was clean, linear, and consistent. A Cepheid's period told you its true luminosity, as reliably as reading it from a label. The significance of this was immense, though Leavitt expressed it with characteristic understatement. Because all the Cepheids in the small Magellanic Cloud sat at roughly the same distance from Earth, the differences in their apparent brightness directly reflected differences in their true brightness. The period luminosity relation was not just a pattern, it was a tool. If you could measure a Cepheid's pulse anywhere in the sky, in any galaxy, at any distance, you could determine its actual brightness. Compare that to how bright it appeared from Earth, and the difference told you how far away it was. The principle was identical to judging the distance of a street lamp by its dimness, but applied across millions of light years. For the first time, astronomers possessed a reliable way to measure cosmic distances far beyond the reach of parallax. Leavitt almost certainly understood the reach of what she had uncovered, but her position did not allow her to pursue it. It was left to others to pick up the key she had cut and use it to unlock doors she would never walk through. Edwin Hubble relied on her period luminosity relation to prove that the Andromeda Nebula was not a cloud of gas within the Milky Way, but an entirely separate galaxy, millions of light years beyond our own. That single finding, made possible by Leavitt's work, expanded the known universe by a factor of thousands in a single step. Today, every measurement of the Hubble constant, on both sides of the tension, descends from her discovery. The Cepheids that Adam Rees's team observes through the Hubble Space Telescope and the James Webb Space Telescope still obey the same relationship Leavitt identified on glass photographic plates more than a century ago. The period still reveals the brightness. The brightness still reveals the distance. The tool has not changed. Only the telescopes pointed at it have. There is something quietly remarkable in that. The universe does not choose its audience. It does not care about titles or institutions or who holds the funding. It revealed one of its most fundamental relationships to a woman the scientific establishment of her time barely acknowledged, working in a basement office in Cambridge, Massachusetts, sorting through the light of stars she would never see with her own eyes. It did not need someone powerful. It needed someone careful enough to notice. There is another way to measure how fast the universe is expanding, and it does not use the distance ladder at all. It does not rely on Cepheids or supernovae or any object in the modern sky. Instead, it looks backward, all the way backward, to the very first light the universe ever released. To understand where that light came from, you have to imagine the universe as it was roughly 380,000 years after the Big Bang. That sounds like a long time. It is not. On the scale of cosmic history, it is the first heartbeat. And the universe at that age was nothing like the one we know. There were no stars, no galaxies, no planets, no molecules, no solid ground of any kind. Space was filled with a dense, blinding fog, a plasma of charged particles and radiation so hot and so thick that light could not travel through it. Photons ricocheted endlessly off free electrons, scattered in every direction, trapped. The universe glowed, but the glow had nowhere to go. If you could somehow stand in that infant cosmos, you would see nothing. Not darkness, the opposite. An all-encompassing white, featureless and scalding, stretching in every direction without boundary or horizon. It was like being inside a furnace with no walls, no floor, no way to tell where you were or how far anything extended. Every point in space was the same. Every direction was opaque. Then the temperature dropped below a critical threshold, roughly 3,000 degrees, and something irreversible happened. Electrons, which had been too energetic to be captured, slowed enough to bind with protons. Atoms formed, hydrogen mostly, some helium. And in that moment, for the first time in the history of existence, the fog cleared. Photons that had been trapped for hundreds of thousands of years were suddenly free. Light streamed outward in every direction, filling the entire universe in a single silent flash. The cosmos went from opaque to transparent in what amounted to a cosmic instant. That light is still travelling. It has been moving through space for nearly 14 billion years, stretched by the expansion of the universe from its original visible glow into the microwave range. Wavelengths far too long for the human eye, but perfectly detectable by the right instruments. It arrives from every direction in the sky, a faint, almost perfectly uniform hum of radiation with a temperature of just 2.725 degrees above absolute zero. It is called the cosmic microwave background, and it is the oldest signal in existence, a fossil, a photograph of the universe as an infant, taken in the light of its very first morning. Arno Penzias and Robert Wilson stumbled upon it in 1964, working at Bell Labs in New Jersey with a large horn antenna originally built for satellite communications. They could not get rid of a persistent, low-level noise in their detector. It came from every direction. It did not change with the seasons. It was not the sun, not the galaxy, not interference from New York City. It was the remnant glow of creation itself, picked up by an antenna that was never designed to find it. They won the Nobel Prize. Decades later, the European Space Agency's Planck satellite mapped this ancient light with a precision that would have been inconceivable to Penzias and Wilson. Between 2009 and 2013, Planck measured tiny fluctuations in the temperature of the cosmic microwave background. Variations of barely 1 part in 100,000. Hot spots and cold spots scattered across the entire sky in a pattern that looks random but is not. Those fluctuations carry information. They are the fingerprints of the physics that governed the early universe. The density of matter, the density of energy, the geometry of space, and critically, the rate at which the universe was expanding when that ancient light was released. From those patterns, using the standard model of cosmology, physicists can do something extraordinary. They can calculate what the Hubble constant should be today, not by observing the modern universe directly, but by winding the clock forward from the infant cosmos, applying the known laws of physics step by step through 14 billion years of expansion, cooling, and structure formation, and predicting where the expansion rate should have arrived by now. The model that performs this calculation is called lambda CDM. It is the most successful cosmological framework ever constructed. Its predictions match the CMB data to an almost absurd degree of accuracy. It accounts for the relative abundances of hydrogen and helium, the clustering of galaxies, the geometry of space. it is by nearly every measure a triumph. And the number it returns for the Hubble constant is 67.4 kilometers per second per megaparsec. Precise. Confident. Confirmed by multiple independent analyses of the same data. It is also by a margin that has refused to close. Too slow. Adam Rees had already changed our understanding of the universe once before he turned his attention to the Hubble constant. In 1998, leading a team called the High Z Supernova Search, Rees helped make one of the most startling discoveries in the history of cosmology. By tracking the brightness of Type 1a supernovae in distant galaxies, his team showed that the expansion of the universe is not slowing down, as nearly everyone expected. It is speeding up. Some unknown energy pervading all of space, was pushing the cosmos apart with increasing force. It was given the placeholder name dark energy, a confession of ignorance dressed as a label. The discovery earned Rees, along with Saul Perlmutter and Brian Schmidt, the Nobel Prize in Physics in 2011. But the project that would define the next phase of his career was quieter, more methodical, and in its own way, more dangerous. It was called SHOES, supernova H0 for the equation of state, and its goal was not to discover something new. It was to measure something old with unprecedented precision, the Hubble constant. The same number astronomers had been arguing over for decades. The method was straightforward in principle, punishing in practice. Rees and his team identified galaxies close enough to contain Cepheid variable stars that the Hubble Space Telescope could observe clearly. They measured those Cepheids, their periods, their brightnesses, and used Leavitt's period luminosity relation to calculate distances. In several of those same galaxies, Type 1a supernovae had recently been observed. This overlap was the key to the entire project. With the Cepheid-derived distances in hand, the team could calibrate the true peak brightness of those supernovae with real precision. And once that brightness was anchored, every Type 1a supernova observed anywhere in the wider universe became a reliable distance marker. Combine those distances with redshifts, and the Hubble constant emerges. The project took years. Each observation had to be agonizingly precise. Cepheids in other galaxies are faint. They sit in crowded stellar fields where their light blends with neighbouring stars. Extracting a clean measurement requires extraordinary care, and Rees's team applied it across more than 40 galaxies, building the most robust local distance ladder ever assembled. The number they arrived at was 73.04 kilometers per second per megaparsec, with an uncertainty of just over 1%. At first, the gap with Planck's 67.4 looked like it could be statistical noise. The uncertainties on both sides were wide enough that they overlapped, just barely. But as Planck refined its analysis and SHOES tightened its measurements, the overlap vanished. The error bars pulled apart. By 2019, the disagreement had reached 4.4 sigma, strong evidence of a real discrepancy. By 2022, with additional Cepheid observations and the largest ever supernova dataset from the Pantheon Plus catalogue, it crossed 5 sigma. 5 sigma is not a number that gets thrown around casually in physics. It is the threshold that particle physicists use to claim a new discovery. The point at which a result is considered so statistically robust that it can no longer be attributed to chance, coincidence, or bad luck. It means the probability that the disagreement between Planck and SHOES is a statistical fluke is less than 1 in 3.5 million. The Higgs boson was announced at 5 sigma. The first detection of gravitational waves was announced at 5 sigma. It is the line in the sand where science stops hedging and says, "This is real, something is happening." The history of the Hubble constant has always been contentious. For decades, two titanic figures, Alan Sandage and Gerard de Vaucouleurs, fought bitterly over its value. Sandage, working from the same Mount Wilson observatory where Hubble had made his original discovery, championed a lower number, around 50. De Vaucouleurs, a French-born astronomer working at the University of Texas, insisted it was closer to 100. The gap between them was enormous. It implied two fundamentally different ages for the universe, and their disagreement lasted the better part of 40 years. It was often personal. Conferences became battlegrounds. Papers were written as much to rebut as to discover. Eventually, better telescopes and better data settled the question. Sandage's value turned out to be too low. De Vaucouleurs was too high. The truth sat between them, and the community moved on. But this time is different. This time, both sides have instruments of extraordinary precision. Both have been scrutinized by the global community, and both refuse to move. 67 from the beginning of time, 73 from the stars and galaxies around us. The gap is not closing, it is hardening, and that changes everything. So here is where things stand. Two completely independent methods have measured the same fundamental property of the universe. One looks backward to the oldest light in existence and uses the physics of the early cosmos to predict what the expansion rate should be today. It returns 67.4. The other looks outward at the modern universe, measuring the distances and velocities of galaxies using the best tools observational astronomy has ever produced. It returns 73. Both have been checked. Both have been challenged. Both have been refined over years by separate teams using different instruments, different calibration strategies, different assumptions. Neither side has budged. The numbers have not drifted toward each other. If anything, as the measurements have improved, they have drifted further apart. The uncertainties have shrunk, and the gap has crystallized into something hard and unyielding. This is the Hubble tension. And what makes it so deeply unsettling is not simply that two numbers disagree. It is what their disagreement implies about the framework that connects them. The standard model of cosmology, lambda CDM, is not a rough sketch. It is one of the most precisely tested theoretical structures in all of science. It rests on a small number of ingredients. Ordinary matter, the kind that makes up stars and planets and human bodies. Dark matter, invisible and abundant, which shapes the gravitational scaffolding of the universe. Dark energy, the mysterious force driving the accelerating expansion. And the assumption that general relativity accurately describes gravity on the largest scales. From these ingredients, lambda CDM predicts the behavior of the cosmos from its earliest moments to the present day. It matches the patterns in the cosmic microwave background with extraordinary fidelity. It predicts the abundance of light elements forged in the first minutes after the Big Bang. It accounts for the large-scale clustering of galaxies across billions of light years. By almost every test we have been able to devise, lambda CDM works. It is not a guess. It is a framework that has earned its authority through decades of prediction and confirmation. And that is precisely why the Hubble tension matters. Because when you take lambda CDM and run it forward from the infant universe to today, the expansion rate it predicts is 9% slower than what we actually observe. The model does not miss by a vague margin. It misses with confidence. Planck's measurement has an uncertainty of less than 1%. Schu's measurement has an uncertainty of just over 1%. The disagreement between them now stands at more than 5 standard deviations, 5 sigma. In the language of statistics, that means the probability of this discrepancy arising by pure chance is less than 1 in 3.5 million. It is the same threshold that was used to announce the discovery of the Higgs boson and the first detection of gravitational waves. When a result reaches 5 sigma, the scientific community no longer treats it as a fluctuation. It treats it as a fact that needs an explanation. And the explanation, for now, does not exist. The tension is not between two laboratories, it is not between two personalities or two philosophies of measurement. It is between the universe as it was and the universe as it is. Between a prediction drawn from the physics of the first 400,000 years and an observation drawn from the physics of the last few billion. Something in that chain, some assumption, some mechanism, some piece of the story we have not yet identified, is either missing or wrong. The model that predicted so much, so accurately, for so long, has encountered a measurement precise enough to find the place where it breaks. That is not a minor footnote. In the history of physics, the moments that mattered most were not the moments of triumph. They were the moments when a trusted framework met a stubborn fact that it could not absorb. Newtonian gravity worked beautifully for 2 centuries before the orbit of Mercury revealed something it could not explain. Classical physics described the everyday world with supreme confidence before black body radiation forced a rethinking of reality at the smallest scales. In each case, the crack was small. The consequences were not. The Hubble tension has that shape. A gap of 9%. 2 numbers that should agree and do not. And on the other side of that gap, something we have not yet learned how to see. The first instinct of any scientist confronted with 2 contradictory measurements is simple. One of them must be wrong. Find the error, fix it, move on. And so, before anyone was willing to entertain the possibility that the standard model of cosmology might be incomplete, the community did what it always does. It went looking for the mistake. Every calibration, every assumption, every step in both measurement chains was re-examined with the kind of thoroughness that borders on obsession. If there was a hidden systematic error lurking somewhere in the data, a bias in the distance ladder, a flaw in the CMB analysis, a subtle contamination that no one had noticed, this was the effort that would find it. One of the most prominent challenges came from Wendy Friedman. Friedman is one of the most experienced distance ladder astronomers alive, and she was not convinced that the Cepheid-based measurements were as clean as the SHOES team claimed. Her concern was specific. Cepheids in other galaxies are observed in crowded stellar fields. Their light can blend with the light of neighbouring stars, making them appear brighter than they truly are. If that blending was systematic, if it biased the brightness measurements consistently upward, the resulting distances would be too short, and the Hubble constant derived from them would be too high. To test this, Friedman turned to a completely different standard candle, the tip of the red giant branch. Red giant stars, when they reach a specific stage in their evolution, hit a maximum brightness that is remarkably uniform. They do not pulse like Cepheids. They do not require the same elaborate calibration chain. They offer a genuinely independent path to the same destination. Friedman's early results using this method suggested a Hubble constant, somewhere between Planck's 67 and Ries's 73. If confirmed, the tension might dissolve. The community watched closely. Then the James Webb Space Telescope changed the terms of the debate. Ries's team secured observing time on Webb and used its infrared instruments to look at the same Cepheids that the Hubble Space Telescope had measured years earlier. The advantage was decisive. Webb's sharper optics could resolve individual stars in crowded fields that Hubble saw as blurs. If the old measurements had been contaminated by blending, Webb would reveal it. It did not. The Cepheids observed by Webb matched the Hubble Space Telescope measurements almost exactly. The calibration held, the distances held. 73 stood. Friedman, however, had also secured time on Webb. Her team used it to measure distances via the tip of the red giant branch, and a newer method using what are called JAGB stars, a class of carbon-rich giants in the J-band of infrared light. The results were more ambiguous than either side might have hoped. Some analyses of Friedman's Webb data supported a lower Hubble constant, closer to Planck. Others found values consistent with shoes. The interpretation depended on choices in the analysis pipeline, how the stellar populations were selected, how the photometry was calibrated, how the backgrounds were subtracted. No consensus emerged. The debate sharpened rather than settled. Meanwhile, other teams had been quietly building measurement methods that bypassed the distance ladder entirely. The Holy Cow collaboration, led by Sherry Suyu, used gravitational lensing, the bending of light around massive galaxies, to measure distances to distant quasars. When a quasar's light passes close to a foreground galaxy, it splits into multiple images, each following a slightly different path through curved space-time. The images arrive at slightly different times. That time delay, combined with a model of the foreground galaxy's mass, gives you the distance. No Cepheids, no supernova, no ladder. Holy Cow's result: 73.3. Consistent with shoes. Independent of it. The Megamarsa Cosmology project took yet another approach. Water molecules orbiting supermassive black holes in distant galaxies emit a specific frequency of microwave radiation. By mapping the geometry and velocities of these orbiting masers, astronomers can calculate a direct, geometric distance to the galaxy. No standard candles needed, no rungs to climb. Their result, while carrying larger uncertainties, also favoured the higher end. Simon Birrer and the TD Cosmo collaboration went further still, refining the lensing technique to address a known weakness called the mass sheet degeneracy, the possibility that certain assumptions about the foreground galaxy's mass distribution could bias the result. Even with these corrections, the lensing measurements continued to point toward a Hubble constant above 70. One by one, the possible errors had been tested. The Cepheid calibration had been confirmed by the most powerful space telescope ever built. An independent standard candle had produced ambiguous but not contradictory results. Two entirely separate methods, using physics unrelated to the distance ladder, had arrived at the same neighbourhood. The error, if it existed, had eluded every attempt to find it, which left a far more uncomfortable possibility. What if the measurements are all correct? What if there is no error? What if the universe is simply not doing what the model says it should? If the measurements are right, all of them, on both sides, then the thing that must be wrong is the bridge between them. Lambda c dm, the model itself. This is not a conclusion anyone arrives at lightly. Lambda c dm has survived every observational test thrown at it for a quarter of a century. It predicted the patterns in the cosmic microwave background before Planck confirmed them. It predicted the large-scale distribution of galaxies before surveys mapped them. Abandoning it, or even modifying it, means changing something fundamental about how we understand the universe works. But the tension demands it. If 67 and 73 are both correct, then somewhere in the 14 billion years of cosmic evolution that lambda CDM describes, something happens that the model does not account for. The leading candidate is an idea called early dark energy, proposed in detail by Vivian Poulin and collaborators in 2019. The concept is deceptively precise. Just before the moment when the cosmic microwave background was released, a new form of energy briefly dominated the universe. Not ordinary matter, not radiation, not the dark energy we observe today. A scalar field. A quantity that fills all of space and carries energy, temporarily boosting the expansion rate before diluting away and vanishing as though it had never existed. If this burst of energy existed, it would have made the early universe expand slightly faster than lambda CDM predicts. That faster early expansion would shift the patterns in the CMB just enough to change the prediction for today's Hubble constant, raising it from 67 towards 73. The tension dissolves, the measurements agree, and the price is a new ingredient in the cosmic recipe, one that existed for a brief period in the deep past and left no obvious trace in the modern universe. The appeal is clear. Early dark energy touches nothing in the late universe. It does not require changing how gravity works or how dark matter behaves. It solves the problem at its source, in the physics of the early cosmos, and then quietly disappears. But the difficulty is equally clear. The field must activate at precisely the right moment. It must carry precisely the right amount of energy, and it must dilute away cleanly without disrupting the other predictions that lambda CDM gets right. That level of fine-tuning makes physicists uncomfortable. Nature rarely arranges its ingredients so conveniently. Mark Kamiankowski, a theorist at Johns Hopkins, and Adam Rees jointly reviewed the state of early dark energy in 2023. Their assessment was honest. Early dark energy remains the most promising direction, but it is not a clean solution. It improves the fit in some areas and worsens it slightly in others. The data do not yet strongly prefer it over lambda CDM. It is a candidate, not a verdict. Neil Schoenberg and collaborators attempted something ambitious in 2022, a systematic ranking of every proposed solution to the Hubble tension. They called it the H0 Olympics. Roughly 30 models were tested against the combined cosmological data, CMB observations, supernova catalogues, galaxy clustering measurements, baryon acoustic oscillations. Each model was scored on how well it fit and how many new parameters it required. Most failed outright. They solved the Hubble tension at the expense of breaking something else, worsening the fit to the CMB, or predicting galaxy distributions that did not match observations. Early dark energy survived, but imperfectly. Nothing scored a clean victory. Other theorists explored the opposite end of the timeline. Instead of modifying the early universe, what if the problem lies in the late universe? Sonny Vagnozzi examined models in which dark energy is not a constant, but a dynamic quantity that evolves over time. In some models, dark energy grows stronger. In others, it crosses a theoretical boundary called the phantom divide, where its equation of state takes on values that classical physics considers forbidden. These models can raise the predicted Hubble constant, but they come with their own costs and their own fine-tuning problems. Perhaps the most intellectually provocative proposal came from Jeremy Sackstein and Mark Trodden, who in 2020 suggested a direct link between early dark energy and the mass of neutrinos. Neutrinos are among the most abundant particles in the universe, yet their mass remains one of the deepest unsolved problems in particle physics. Sackstein and Trodden showed that certain forms of early dark energy naturally couple to the neutrino sector, meaning that resolving the Hubble tension could simultaneously constrain, or even determine, the mass of the neutrino. If correct, it would mean that a disagreement between two telescopes is connected to the behaviour of the smallest known particles in nature. The tension would not just be a cosmological puzzle, it would be a bridge between the physics of the very large and the physics of the very small. None of these proposals has been confirmed. None has been ruled out. What is clear is that the tension cannot be absorbed by a minor tweak. Whatever resolves, it will change something substantial about our picture of the universe, either what it contained in its earliest moments, or how its dominant energy behaves today, or something else entirely that no one has yet imagined. The universe is not obligated to make this easy. It never has been. The Hubble tension is not alone. It is the loudest of a growing set of disagreements between what the early universe predicts and what the late universe reveals. But it is not the only one. And the fact that it has company makes it harder to dismiss as a fluke and harder to solve with a single narrow fix. The most prominent companion is called the S8 tension. S8 is a parameter that describes how clumpy the distribution of matter is in the universe, how strongly matter clusters together under the pull of gravity at the largest scales. Lambda CDM, using the cosmic microwave background, predicts a specific degree of clumpiness. When astronomers measure the actual distribution of matter in the modern universe using galaxy surveys and gravitational lensing, they find something slightly but persistently different. The local universe is smoother than the model expects. Matter has not clustered quite as tightly as Lambda CDM says it should have. Taken on its own, the S8 tension is less statistically severe than the Hubble tension. It hovers around 2 to 3 sigma. Noticeable, worth watching, but not yet at the threshold where the community would call it a discovery. But the pattern it traces is striking. The early universe, as captured by the CMB, predicts a cosmos that expands at a certain rate and clusters at a certain strength. The late universe, as observed directly, expands faster and clusters less. Both discrepancies point in the same direction. Both suggest that something between then and now does not follow the script. This raises an uncomfortable question. If Lambda CDM was simply carrying a small calibration error or a single incorrect assumption, you might expect the discrepancy to show up in one measurement but not others. The fact that multiple independent observations are all pulling away from the model's predictions in a coherent direction suggests something more systematic. Not a mistake in one measurement, but a gap in the framework itself. Some researchers have asked whether the local universe might simply be unusual. If the Earth happened to sit inside a large, unusually empty region of space, a cosmic void, the local expansion rate would naturally appear faster than the global average, just as a bubble rises faster than the water around it. It is a tidy explanation. It requires no new physics. W. Darcy Kenworthy, Dan Skolnick, and Adam Rees tested it directly, examining whether the galaxies used to measure the local Hubble constant showed any signature of living inside such a void. They found none. The local universe looks statistically ordinary. The expansion rate is not a trick of our position. It is a property of the cosmos as a whole. Others have considered whether the problem might lie not in the contents of the universe, but in the rules that govern them. Modified gravity, alterations to general relativity that become significant only on the very largest cosmological scales, could, in principle, change both the expansion rate and the clustering of matter without conflicting with any experiment we have conducted on smaller scales. we have tested general relativity with extraordinary precision in the solar system, in binary pulsars, in the detection of gravitational waves. It passes every time. But those tests all probe scales of billions of kilometres at most. The Hubble tension asks about the behaviour of gravity across billions of light years. We have remarkably little direct evidence that the rules work the same way at both extremes. This is the quiet question at the centre of it all. We have spent a century assuming that the laws of physics are identical everywhere and at every time. It is one of the deepest assumptions in science, so deeply embedded that it barely registers as an assumption at all. The Hubble tension does not prove it wrong, but it asks, with increasing statistical force, whether we have ever tested it precisely enough to be certain. And the honest answer is that we have not. Every great advance in cosmology has come from a measurement that refused to match the prevailing model. The expansion of the universe was discovered that way. Dark energy was discovered that way. The pattern is clear. A fact that does not fit is not a failure. It is an invitation. And the Hubble tension has the shape of an invitation that the universe has issued before. The question will not remain open forever. A generation of instruments is already being built, or has already begun operating, that will measure the expansion rate with a precision and independence that should either confirm the tension beyond any remaining doubt or reveal the subtle error that has eluded everyone so far. Within a decade, the ambiguity will almost certainly break in one direction or the other. The first results are already arriving. The Dark Energy Spectroscopic Instrument, DESI, is mounted on a telescope in Arizona and has been mapping the three-dimensional positions of millions of galaxies and quasars since 2021. Its goal is to trace the expansion history of the universe across 11 billion years using baryon acoustic oscillations. A faint, regular pattern imprinted on the distribution of galaxies by sound waves that rippled through the early cosmos. In 2024, DESI released its first major set of cosmological results. The findings were preliminary but striking. The data hinted that dark energy may not be constant. If confirmed, it would be exactly the kind of late universe physics that some theoretical models of the Hubble tension predict. The European Space Agency's Euclid telescope, launched in 2023, is surveying a third of the sky with the goal of mapping both the geometry of space and the growth of cosmic structure with unprecedented clarity. Euclid combines visible and infrared imaging to measure the shapes of billions of galaxies, tracing how their light is bent by the gravitational influence of the dark matter between them. If dark energy is evolving, if it is not the steady, unchanging force that lambda CDM assumes, Euclid is designed to detect that evolution directly. NASA's Nancy Grace Roman Space Telescope, expected to launch later this decade, will bring a different kind of firepower. Roman will observe thousands of Type 1a supernovae and Cepheid variable stars across a wide swath of the cosmos, building a distance ladder of a scale and precision that dwarfs anything currently possible. If there is a systematic error hiding in the existing distance measurements, something too subtle for the Hubble Space Telescope, or even Webb to catch, Roman's sheer statistical power should expose it. But perhaps the most exciting prospect comes from a method that sidesteps every traditional technique entirely. When two neutron stars spiral into each other and collide, they produce gravitational waves, ripples in the fabric of space-time, that carry information about the distance to the event encoded directly in their amplitude. If the collision also produces light, the redshift of that light gives the velocity. Distance and velocity. The two ingredients for the Hubble constant, delivered in a single event, with no ladder, no standard candle, and no cosmological model required. Astronomers call these events standard sirens. The first one was observed in 2017. LIGO and Virgo have already used it to make a rough measurement of the Hubble constant. The uncertainty is still large, but as detectors improve and more events are observed, the precision will sharpen. LISA, the European Space Agency's space-based gravitational wave observatory planned for the mid-2030s, will extend the reach of standard sirens to cosmological distances, providing a completely independent measurement that answers to no assumptions except the physics of general relativity itself. On the ground, the Simons Observatory in Chile's Atacama Desert and the planned CMBS-4 experiment will map the cosmic microwave background at higher resolution and greater sensitivity than Planck achieved. If early dark energy left even the faintest fingerprint on the CMB, a subtle distortion in the power spectrum, a shift in the damping tail, these instruments are built to find it. The convergence is coming. Within 10 years, half a dozen independent methods, each using different physics, different instruments, and different assumptions, will deliver their own measurements of the Hubble constant. If they cluster around 73, the tension is real, and lambda CDM will need to change. If they scatter, the mystery deepens. Either way, the era of ambiguity is ending. The instruments are already in the sky, already taking data, already beginning to answer the question that has haunted cosmology for more than a decade. The history of cosmology is a history of humility. In the 1920s, the universe was static. It had always existed and would always exist, unchanging in its broad structure, a permanent stage on which the stars performed their slow routines. Then Lemaitre published his equations, and Hubble pointed his telescope, and the stage itself began to move. The universe was expanding. The static picture, held with absolute confidence for centuries, was wrong. In the 1990s, the expansion was slowing down. Gravity, it was assumed, would eventually bring the growth to a halt, perhaps even reverse it. The universe would decelerate, plateau, and maybe one day collapse back on itself. It was a tidy narrative, a beginning, a middle, and one of two possible endings, an eternal coast or a final contraction. Then two teams tracked the fading light of distant supernovae and found that the expansion is not slowing at all. It is accelerating. Something, dark energy, a force no one had predicted and no one could explain, was pushing the cosmos apart with increasing urgency. The decelerating picture, held with quiet confidence for decades, was wrong. The ending, whatever it would be, had not been written yet. Each of these revisions followed the same pattern, a model that matched the available data beautifully, a new measurement, more precise than anything that had come before, and a result that did not fit. The discrepancy was always small at first, always met with skepticism, always examined for error, and in each case, the error turned out not to be in the data. It was in the model, that the universe was doing something the prevailing theory had not accounted for, and the only way to find out was to measure carefully enough to catch it. The Hubble tension carries that same quiet energy. Two numbers that should agree, both measured with care that borders on devotion. Both checked, challenged, refined, and checked again. Both standing firm. 67.4 from the oldest light in existence, predicted by the most successful model in the history of cosmology. 73.04 from the stars and galaxies we can see, measured by some of the most precise instruments ever built. A gap of 9% that has survived everything the scientific community has thrown at it. It may still close. A systematic error may yet be found, hiding in a corner no one has thought to look. A new analysis may reveal that the C-feeds were subtly biased, or the CMB was misread, or the statistics were less decisive than they appeared. Science has surprised itself before, and the tension may dissolve as quietly as it arose. If so, the textbooks will record it as a decade-long lesson in the difficulty of precision measurement, and cosmology will move on with lambda CDM intact. But if it does not close, if the instruments now being built confirm what the current instruments have found, then something about our understanding of the universe will have to change. Not a detail, not a footnote, something structural. Something in the physics that connects the beginning of time to the present moment. A new field that flickered to life before atoms formed. A dark energy that refuses to sit still. A rule we thought was universal that turns out to have limits we never tested. Whatever it is, it will have been waiting in the gap between two numbers that a century of astronomy could not reconcile. The universe is under no obligation to be simple. It is under no obligation to match our expectations, or to organise itself around the models we have built to describe it. When it does not, the question is not what went wrong. The question is what we have not yet understood. Two numbers, both correct, both irreconcilable. 67 from the beginning, 73 from the world around us, and somewhere in that 9%, hidden in a gap that should not exist between two answers that should have been the same. The next chapter of physics is waiting to be read.